So, oh, I forgot about this one. So, there are actually two more. So I want to just quickly show you, okay. So this is a gorgeous experiment. Remember I told you the story of the guy with the boat and the opaque wall? And it turns out that's a cheat. It turns out that that this opaque screen doesn't actually give you quantum mechanically isolated photons. They're still, in a very important way, classical. So this experiment was done truly with a source that gives you quantum mechanically isolated single photons one at a time. So this is the analog of the Hitachi experiment. And it was done by this pretty awesome Japanese group some number of years ago. And I just want to emphasize that it gives you exactly the same effects. We see that photon, this should look essentially identical to what we saw at the end of the Hitachi window. And that's because it's exactly the same physics. It's a grating with something like 10 slits, and individual particles going through one at a time and hitting the screen and going bing. So what you see is the light going bing on the CCD. Pretty spectacular experiment. Okay, so let's get back to electrons. I want another probe of whether electrons are really waves or not. So this other experiment, again, you're going to study this on your problem set. This other experiment was done by a couple of characters named Davison and Germer. And in this experiment, what they did is they took a crystal, and a crystal is just a lattice of regularly located ions. Diamond. Yeah. Is what different? You mean for different electrons? Well, they can be different if the initial conditions are different. But they could be, if the initial conditions are the same, then the probabilities are identical. Yeah, so every electron behaves identically to every other electron. Is that what you were asking? Yeah. Sure, oh, absolutely. So the issue there is just a technological one of trying to build a beam that's perfectly collimated. And that's just so there's always some dispersion. So in practice, it's very hard to make them identical. But in principle, they could be if you were infinitely powerful. Again, I was banned from the lab, so it's not so here's our crystal. You can think of this as diamond or nickel or whatever. I think they actually use nickel, but I don't remember exactly. And they sent in a beam of electrons. When they send in a beam of electrons, and what they discover is that if you send in these electrons, and watch how they scatter at various different angles. I'm going to call the angle here of scattering theta. What they discover is that the intensity, the intensity of the reflected beam as a function of theta shows interference effects. And in particular, they gave a whole calculation for this, which I'm not going to go through right now, because it's not terribly germane for us. You're going to go through it on your problem set, but that'll be good, and it's a perfect thing for your recitation circuit to go through. But the important thing is the upshot. So if the distance between these crystal planes is L, D. The distance between the crystal planes is D. What they discover is that the interference effects that they observed, these maxima and minima, are consistent with the wavelength of light, with the electrons behaving as if they were waves, with a definite wavelength, with the wavelength lambda being equal to some integer n over 2d sine theta. So this is the data these are the data they actually saw. These are the data they actually saw. And they infer from this that the electrons are behaving as if they were wave-like with this wavelength. And what they actually see are individual electrons hitting one by one, although in their experiment they couldn't resolve it. But that is what they see. And so in particular, plugging all this back into the experiment, you send in the electrons with some energy which corresponds to some definite momentum. This leads us back to the same expression as before, that the momentum is equal to h over lambda with this lambda associated. So it turns out that this is correct. So the electrons diffract off the crystal as if they have a momentum, which comes with a definite wavelength corresponding to its momentum. So that's experimental result. Oh, I forgot to check off 4. That's experimental result 5, that electrons diffract. We already saw the electron diffraction. So something to emphasize is that, so these experiences we've described them were done with photons and with electrons, but you could imagine doing the experiments off of them. This is, of course, hard. Quantum effects for macroscopic objects are usually insignificantly small. However, this experiment was done with buckyballs, which are the same shape as soccer balls, in some sense, but they're huge, they're gigantic objects. Okay, here's the experiment in which this was actually done. These guys are just totally, so this is Zellinger's lab, and it doesn't look like, I mean, it looks kind of, it's hideous, right? To a theorist, it's like, come on, you've got to be kidding. But here's here's what a theorist is happy about, because it looks simple. We really love lying to ourselves about that. So here's an oven. We're going to cook up some buckyballs and emit them with some definite known thermal energy, known to some accuracy. We're going to collimate them by sending them through a single slit, and then we're going to send them through a diffraction gradient, which again is just a whole bunch of slits. And then we're going to image them using photoionization and see where they pop through. So here is the horizontal position, this way along the grading, and this is the number that comes through. So literally one by one count, because they're going bing, bing, bing as the C60 molecule goes through. So without the grading, you just get a peak, but with the grading, you get these side bands, you get interference fringes. So these guys, again, they're going through one by one. A single buckyball, 60 carbons, going through one by one, is interfering with itself. This is a gigantic object by any sort of comparison to single electrons. And we're seeing these interference fringes. So this is a pretty tour de force experiment, but I just want to emphasize that if you could do this with your neighbor, it would work. You just have to isolate the system well enough. And that's a technological challenge, but not a principal one. Okay. Yeah, good. Okay. So we have one last experimental fact to deal with, and this is Bell's inequality. And this is my favorite one. The Bell's inequality for many years languished in obscurity until someone realized that it could actually be done beautifully in an experiment that led to a very concrete experiment that they could actually do and that they wanted to do. And we now think of it as an enormously influential idea which nails the coffin closed for classical mechanics. And it starts with a very simple question. I claim that the following inequality is true. The number of people in the room who are undergraduates, which I'll denote as U, and not blonde, which I will denote as bar B. So undergraduates who are not blonde. Actually, let me write this up. Number who are undergrads and not blonde